morning all. This is Dr. D. Khalandar Basha working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the signal description of 8086 microprocessor. The slides are prepared by referring the textbook Advanced Microprocessor and Peripherals. Authors K.M. Burchandi and IARE. Publication Tata McGraw. The figure shows the various pins exist in 8086 processor for both maximum mode and minimum mode. Most of the signals are common for maximum mode as well as minimum mode. Wherever we are showing these are for minimum mode, the corresponding signals here which are having these are for maximum mode. The remaining signals are common for both the minimum and maximum mode. The 8086 processor is a 16-bit CPU available in 3 different clock cycles, that is 5 MHz, 8 MHz and 10 MHz. It is available in 40-pin package with a DIP package. The 8086 operate in a single processor or multi-processor configuration to achieve high performance. If 8086 processor operate as a single processor, it is called as minimum mode. If the 8086 processor is configured as multi-processor configuration, then the processor is said to be in maximum clock signal. This clock signal is an input for 8086 processor. Here we have a clock signal with the pin number 19. The clock input provides the basic timing for processor operation and bus control activity. It's an asymmetric wave with 33% duty cycle and it is square wave. The range of frequency for a different 8086 processor varies from 5 MHz to 10 MHz. The second signal we are going to discuss is the reset signal. The processor to terminate the current activity and start execution from FFF0H. So out of 1 MB of memory, whenever the system is reset, the program which is exist at the address FFF0H will be executed. The signal must be active for at least 4 clock cycles to reset the processor. It restart execution when the reset returns to low. A reset is internally synchronized with the clock signal. The next signals we are having are AD0 to AD15, which are address and data lines. These are multiplex signal which are of 16 in number. Multiplex signal means these signals carry both address as well as data information. And these signals are used for memory and I/O address and data lines. The address remains on the lines during T1 state, while the data is available on the data bus during T1, T2, T3 and T4 clock pulses, where the T1, T2, T3, T4 clock pulses are considered as one mission cycle. So out of these 4 clock pulses, T1, T2, T3 and T4, during T1 period we are going to have address information. In the rest of the portion we are going to have data information. For differentiating whether it is address information or data information, we have one more signal that we will see in detail later. That signal is ALE signal. So when ALE signal is 1, when ALE signal is equivalent to 1, it indicates the AD0 to AD15 contains the address information. If the ALE signal is equivalent to 0, then the AD0 to AD15 is consist of the data information on the lines AD0 to AD15. The next signals we are having are A19 to A16 or S6 to S3. These are status signals and address signals. These are time multiplexed address and status line. During T1, these are most significant address lines of the memory operation, as 8086 processor is consist of 20 address lines. The data lines are 16 lines. The AD0 to AD15 will consist of 16 address lines. The left out 4 address lines we can see on the lines A16 to A19. During IO operations, these lines are low. During memory or IO operation, the status information is available on S6 to S3 during T2, T3 and T4 clock pulses. The status of interrupt enable flag will be displayed on the status signal and it updated at the beginning of the each clock cycle. The next signals, that is S4 to S3, these signals are used for indicating which segment address presently the processor is accessing. The values of S4, S3 and which segment registers are accessed by the processor are shown in table 1.1. When S4, S3 are 00, the processor is accessing the alternate data, which is nothing but extra segment. When S4, S3 are 01 respectively, the processor is accessing the stack segment address. When S4, S3 are 10 respectively, either the processor may accessing code segment register or the processor may not be accessing any one of the segment register. When S4, S3 are 11 respectively, the processor is accessing the data segment register. The status line S6 will always goes to low. S5 will indicate what is the interrupt flag we are having, that will be reflected on S5. S3, S4 will be indicated which segment the processor is accessing, either it is code segment, data segment, stack segment or extra segment, or the processor is not accessing any one of the segment. The next signal we are having is ALE, where ALE expands as address latch enable. This signal indicates the availability of a valid address on the address bus and the data on the data lines and is connected to the latch enable input of the latches which are separating address and data information. For a mission cycle, as we know, we are having 4 clock pulses, T1, T2, T3, T4. Out of, during T1, the ALE will be goes to 1, indicates the lines AD0 to AD15 will consist of address information. During T2 to T3 and T4, the ALE signal will be goes to low and the lines AD0 to AD15 will gives the data information. The next signal is BHE bar S7. BHE stands for bus high enabled. S7 is one more status signal. This is active low signal as BHE bar is given with a complement symbol. The bus high enable signal is used to indicate the transfer of data over the higher order data bus, that is on the bits lines D8 to D15 on AD15 to AD8. If the BHE bar signal goes to low for the data transfer over the higher bits, that is D8 to D15, and is used to drive chip select of odd address memory bank or even address memory bank as well as peripherals. The status signal S7 is not used currently in 8086 processor. Next we have the signals are S2, S1, S0, 3 status signals. All these 3 status signals are active low signals. These are used in maximum mode. These status signals indicates the type of operation carried out by the processor. These become active during T4 of the previous cycle and remains active during T1 and T2 of the present cycle or current bus cycle. These status lines are encoded as shown in the table. When S2, S1, S0 are 000, it indicates the processor giving an interrupt acknowledgement on INTA bar. When these signals S2, S1, S0 are 001, it indicates the processor is reading the IO port. When the signals S2, S1, S0 possessing 010 respectively, the processor is doing write the information to IO ports. When S2, S1, S0 are 011, the processor will be in halt state. When S2, S1, S0 are possessing 100, the processor accessing the code. Whenever the S2, S1, S0 signals are possessing 101, the processor is reading the memory. Whenever S2, S1, S0 are having the value as 110 respectively, the processor is writing the data to a memory. Whenever the S2, S1, S0 are 111, the processor will be in passive state. The next signal is INTR, which is an interrupt request to the processor. Any IO device, if they want to interrupt the processor, the interrupt signal can be given to the processor on INTR line. This interrupt signal is sampled during last cycle of each instruction to determine the availability of the request. If any request is pending, the processor enters the interrupt acknowledgement cycle. Once the processor is recognize the interrupt request and the processor is ready for accepting the interrupt, then it will give an acknowledgement to the interrupt raised device. That will be given on INTA bar, where INTA stands for interrupt acknowledgement. This is active low signal. When the INTA bar signal goes to low, it means that the processor has accepted the interrupt which is raised on INTR signal. It is active low during each interrupt acknowledgement cycle. The next signals we are having are HOLD and HLDA. These are related to minimum mode and the processor for DMA access. HOLD, HLDA, where HLDA stands for hold acknowledgement. Hold signal indicates the processor that another master is requesting for bus access. The processor, after receiving the hold request, issued an hold acknowledgement signal on HLDA to the another master which is requested the bus access. This acknowledgement is given in the middle of the next cycle after completing the current bus cycle. The next signals are read and write signals. RD bar, this is read signal which is active low signal. The RD signal indicates the processor is performing either memory or with IO read operation. The read shows the states for T2, T3 of any read cycle. Whenever RD bar is equivalent to 0, it indicates the processor is reading the data, either it may be from memory or IO device. When RD bar is equivalent to 1, it indicates the processor is neither reading the content from memory nor from the IO device. Next status signals we are having is write bar, which is a active low signal, and this is corresponding to write operation by the processor. The write bar signal indicates the processor is performing either memory or IO write operation. This write bar signal shows the state for T2, T3 of any write cycle. If write bar is equivalent to 0, it indicates the processor is performing the write operation with the memory or IO device. If write bar is equivalent to 1, that indicates the processor is not performing write operation either with memory or IO device. The processor cannot accept both read and write bar active low at the same time. Either it can go for read operation or write operation or none of the read and write operations, but both cannot be possible. The next signal we are having is ready signal and test signal we will see here. The ready signal, it is an acknowledgement from slow devices or memory that they have completed the data transfer. As the processor is high speed device compared to either memory or IO device, the rate at which the processor is performing the operation, either it may be read operation or write operation, as these two are not at the same speed, the slow response devices will take more time. So in that case, these slow response devices will give an acknowledgement to the processor indicating whatever the data which the transaction has taken place by the microprocessor have completed. The next signal we are having is test bar, which is active low signal. This signal will be examined by a wait instruction. For each and every mission cycle, we have 4 clock pulses, that is T1, T2, T3, T4. If these 4 clock pulses are not sufficient for any transaction with the processor, then the wait clock pulses will be inserted between T3 and T4 clock pulses. If test pin goes to low as it is active low signal, it indicates the execution will continue, else the processor will be remains in ideal state. The next signal we are having is NMI. NMI stands for non-maskable interrupt. This NMI is an edge-triggered input which causes a type 2 interrupt. The NMI is non-maskable internally by software. So whenever any interrupt is generated and if it is non-maskable interrupt, the processor immediately will execute the ISR corresponding to the NMI interrupt. A transition from low to high initiate the interrupt response at the end of the current instruction. Next, power supplies. The 8086 we are having VCC, a power supply at a voltage of plus 5 volts. This voltage is required for the internal operation of the elements of 8086 for providing bias voltage for the internal elements like transistors and FETs. The ground signal, it is GND. This is for providing a reference node or ground signal for the internal circuit of 8086 processor. The next signal is MN by MX bar, where MN is for minimum mode, MX is for maximum mode. This signal logic level decides whether the processor to be operated in minimum mode and maximum mode. If Mn by Mx bar is equivalent to 1, it indicates the processor is in minimum mode. As we had discussed earlier, the minimum mode means the 8086 standalone, it is doing the operation or executing the current application. So it is a single processor system. When Mn by Mx bar is equivalent to 0, so it indicates the processor is in maximum mode, where the 8086 operating application with co-processor also. That we will call as multi-processor system. The next signal is M by IO bar, which is memory or IO operation, where IO stands for input output operations. When the signal M by IO bar is low, it indicates the CPU is having an IO operation. And if M by IO bar signal is equivalent to 1, it indicates the CPU is having a memory operation. So M by IO bar is 1, it indicates memory operation. Either it may be a memory read or memory write operation. If M by IO bar is equivalent to 0, then it is corresponding to the IO device either read or write operation. So if M by IO bar and read signal and write signal are having the values like this, if M by IO bar is 0, read bar is 0, write bar is 1, then it indicates here we have IO bar is equivalent to 0. That means it is corresponding to IO operation, as read is active low signal and is 0, and write is active low but the value is 1, so it is write is disabled. So this is performing IO read operation. If M by IO bar signal is equivalent to 0, read bar is equivalent to 1, write bar is equivalent to 0, it indicates the processor is performing the IO write operation. If M by IO bar is equivalent to 0, read bar is equivalent to 1, write bar is equivalent to 1, it indicates no IO operation is taking place. Next, when M by IO bar is 1, read bar is equivalent to 0, write bar is equivalent to 1, it indicates it is a memory read operation. If M by IO bar is 1, read bar is equivalent to 1, write bar is equivalent to 0, it indicates the operation is corresponding to memory and it is write operation. So this will indicates it is a memory write operation. If M by IO bar is 1, read bar is equivalent to 1, write bar is equivalent to 1, that indicates there are no transaction with IO, no operation with respect to memory, either it may be read or write operations. The next signal we are having is DT by R bar, where DT by R bar stands for data transmit or receive. This output signal is used to decide the direction of data flow through the transceiver, as the transceivers are bidirectional buffers. When the processor sends out data, this signal will be high and the processor is receiving data when this signal is 0. So if DT by R bar is equivalent to 1, it indicates the data is transmitting by the processor. It is nothing but a write operation. When DT by R bar is equivalent to 0, that means the processor is receiving the data, which is nothing but the processor is performing the read operation. The next signal we are having is DEN bar, where DEN stands for data enable. DEN signal indicates the availability of valid data over the address or data lines. It is used to enable the transceivers, which are bidirectional buffers, to separate the data from the multiplexed address and data signals. It is active from the middle of the T2 until the middle of the T4. Whenever DEN bar is equivalent to 0, it indicates the valid data is present. Whenever DEN is equivalent to 1, it indicates whatever the information which is existing on the data lines, that is address data lines, is not a valid one. The next signals are QS1, QS0. These two signals are used for indicating the status of the instruction queue which is present in 8086 architecture. The 8086 is consist of a instruction queue which is supporting a pipeline mechanism, and the size of instruction queue we are having is 6 bytes. Whenever the processor is executing phase, so the bus is free, then it will fetches the instructions from the code segment which is external to the processor into the instruction queue. The QS1, QS0 lines gives information about the status of the code prefetched queue. These are active during clock cycle, after which the queue operation is performed. The QS1, QS0 encoded are shown in the table. When QS1, QS0 is equivalent to 00, it indicates there is no operation on queue. Whenever QS1, QS0 is 01, it indicates it is accessing the first byte of the opcode from the queue. When QS1, QS0 are 10, it indicates the queue is empty. When QS1, QS0 are 11, it indicates the processor is accessing the subsequent byte from the queue for an instruction. In 8086 processor based system, the instruction queue is 6 bytes because each and every instruction which are exist in the 8086 may occupy 1 memory location or 2 memory location until 6 memory location. It depends upon which instruction we are executing. Either it may occupy 1 memory location, maximum 6 memory location per instruction. The next signals are RQGT0, RQ bar GT bar 1, RQ for request, GT for grant. These pins are used by the local bus master in maximum mode to force the processor to release the local bus at the end of the processor current bus cycle. Each of the pins is bidirectional with RQ and GT0 having highest priority than RQ GT1. The next signal is lock bar, which is an active low signal. The lock signal indicates that other system bus masters will be prevented for gaining the system bus, while the signal, that is lock signal, is low. It is activated by the lock prefixed instruction and remains active until the completion of the next instruction. The lock prefixed instruction ensures that the other processor connected in the system will not gain the control of bus. So in this class we have discussed the various pins which are existing in 8086 processor, which is a 40 pin. First we have discussed address lines, data lines, that is D0, AD0 to AD15, which are address as well as data information. VCC, ground signals are power supplied signals. NMI is non-maskable interrupt. INTR is an interrupt request to the processor. The clock, which is decides the process speed. The higher 4 bits of address lines we can see on A16 to A19. These signals are also consist of the status information S3, S4, S5, S6. BHE bar S7, which is for bus high enable. MN by MX bar to indicate either the processor is in minimum mode or maximum mode. Read bar, read operation. Write bar indicate write operation. RQ by GT, two signals we are having, RQ by GT 0, RQ by GT 1. These are request grant signal in the maximum mode. Hold, HLDA, these are DMA request for the bus access in minimum mode. Hold is a request, acknowledgement is given on HLDA line. M by IO bar, which is memory or IO operation. DT by R bar, which will give the direction of data flow on the receiver, data transmit or receive. DEN indicating the valid data present on the address data bus. ALE, address latch enable, for indicating whether these lines are consist of address information or data information. INTA bar, which is interrupt acknowledgement Upon receiving the interrupt signal on INTR, the acknowledgement given by the processor on INTA bar. The lock signal, it is for restricting the master to access the bus. S2, S1, S0, these are the status signals in the maximum mode. The queue status will be indicated on QS1 and QS0. Test bar signal to indicate either the processor in ideal state or execution phase. Ready signal, it is a status signal given by the slow response device to the processor. Reset, to reset the entire 8086 processor, we have to give this reset signal active high. When the system is reset, the code which is existing at the address FFFF0H, 4F0H, that code will be executed. So in this class, we have discussed the various pins exist in 8086 processor, the significance of each and every pin. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.